Hello everyone, I am Swapnil Patil and the content expert of this lecture is Dr. Kavita Singh. I am here with another interesting and learning episode of the B.Pharm on the important unit of crystallization. Let's begin with our chapter, that is module 1, Introduction to the Crystallization. Let's start with a general introduction. What is meant by crystallization? Crystallization is a chemical solid liquid separation technique in which mass transfer of the solute from the liquid solution to the pure solid crystalline phase occurs. In other words, crystalline can better define. Crystalline is the formation of solid particles within the homogeneous phase. It involves spontaneous arrangement of particles into the repetitive orderly array, that is regular geometric pattern. The liquid can solidify into the crystalline forms whenever attractive forces between the particles are strong enough to overcome the disorderliness. Crystallization differs from the precipitation in that product is deposited from supersaturated solution. Applications of crystallizations when we considered, the main applications are purification of drugs. Recrystallization techniques is used to purify the APIs and excipients. Second most important application is the better processing characteristics. The micromeritics of the drugs such as compressibility, wettability can be modified by the crystallization technique. Third most important, that is the crystalline powders are easy to handle, hence offer the convenience of transportation and storage. Fourth important application, the crystalline form of the molecule exhibits high chemical stability. Therefore, it increases the stability of drug. For example, amorphous penicillin G is less stable than its corresponding crystalline salt. Similarly, amitriptyline is more stable in crystalline form than in amorphous form. Fifth, improved physical stability. In case of suspension, stability and hardness of the tablet is better managed with the crystalline powder in compaction in comparison to the amorphous form. The most important one, improved bioavailability. Crystalline forms have less solubility than their amorphous counterpart, and this may be utilized in improving the bioavailability of the drug that are not stable in the solution. For example, penicillin G in a crystalline form does not dissolve immediately in gastric fluid, thus degradation decreases and bioavailability enhances. The applications also includes sustained release of the drugs can be achieved by incorporating crystalline forms of the drugs. For example, protamine zinc insulin in crystalline form slowly and continuously releases insulin from the site of injection for prolonged periods. Now friends, we will move towards what is nucleation and crystal growth in module 2. After having the brief idea about the crystallization and its applications, we shall move ahead to learn about the concept of nucleation and crystal growth. In the formation of crystals, three major steps are essential. Step 1, that is supersaturation. Formation of concentrated solution. Step 2, that is nucleation. What is meant by nucleation? The birth of new solid particles. Step 3, crystal growth. The growth of nucleus to microscopic size. So let's study in details these three major steps involved in a crystallization process. Step 1, supersaturation. When the solubility of the compound in the solvent exceeds the saturation solubility, the solution becomes supersaturated and the compound may precipitate or crystallizes out. Supersaturations may be achieved through evaporation of the solvent from the solution, or it may be cooling of the solution if the solute has positive heat of solution. The third most important way, that is the formation of new solute as a result of chemical reaction. Another way, that is addition of substance which is more soluble in a solvent than the solid to be crystallized. Now let's move towards the nucleus formation. How the nucleation is there? Nucleation is the process of formation of tiny particles of new phase within a homogeneous supersaturated liquid phase. It is a consequence of rapid local oscillations at the molecular level when the molecules or ions or atoms are in a random motion in any small volume. Initially, several molecules, ions, atoms associated to form clusters or loose aggregates which disappear quickly. When enough particles associate to form an embryo, there is a beginning of lattice arrangement and formation of new solid phase. Embryos have short lives and dissolve soon because they grow to a size that is thermodynamically equilibrium with the solution. The initially formed crystals are of molecular size and termed as nuclei. So we may say that nucleation refers to a birth of very small bodies of new phase within a supersaturated homogeneous existing phase. Nucleation may take the following steps. It might be primary nucleation or secondary nucleation. Then what is meant by primary nucleation? Primary nucleations may be of two types, that is homogeneous nucleation or a heterogeneous nucleation. What is homogeneous nucleation? When the nucleation occurs in a homogeneous solution that is free from any solid particles, the phenomenon is called as homogeneous nucleation. While heterogeneous nucleation is when the macroscopic solid particles called seed are present in a solution, the rate of nucleation becomes rapid. Actually, the solid particles catalyze the nucleation rate by reducing the energy required for the nucleation. Atmospheric dust may act as a seed, and these seeds do not possess the same crystal structure of the solute. Now friends, we will move towards the secondary nucleation. Secondary nucleation, if the nuclei are formed due to the presence of existing macroscopic crystals in the magma, then the nucleation is called secondary nucleation. By the two ways of secondary nucleation occur, that fluid shear nucleation or contact nucleation. What is meant by fluid shear nucleation? When supersaturated solution moves past the surface of growing crystals at a substantial velocity, the shear stresses in the boundary layer may sweep away embryos or nuclei and thus appear as a new crystal. Contact nucleation can occur due to the collision between existing crystals with each other or with the walls of crystallizer and rotary impellers or agitator blades. This usually breaks the microscopic dendritic growth on the surface of a growing crystal to form more clusters and embryos. And finally, this hits the clusters of the solute particles to become organized into the crystals. Now we need to understand how nucleation can begin in the crystallization process. First, that is soft or weak crystals on impact with a moving part in the crystallizer can break into the fragments which acts as a nuclei. Small crystals which are formed in the previous process are added to act as a nuclei. And the third step, in a supersaturated solution or under poor mixing, the needle-like structures are observed on the ends of crystals. And these structures grow faster and come out to give the crystals of poor quality. The third step, that is the crystal growth. How it is occurred? Crystal growth is the diffusion process and surface phenomenon from the solution. Solute molecules or ions reach the faces of crystals by diffusion. On reaching the surface, the molecule ions are accepted by the crystal and organized into the space lattice. This phenomenon continues at the surface at finite rate. Crystal growth takes place into the two steps. The steps are diffusional steps and interfacial steps. Diffusion step includes solid molecules or ions from the supersaturated solution diffuses through the liquid phase to reach the crystal surface. The interfacial step, on reaching the surface, the solid molecules or ions are accepted by the crystal and organized into the crystal lattice. Thermodynamically, a small particle possesses a significantly higher surface free energy per unit mass than larger ones. Hence, the solubility of small crystals are several times higher than the larger ones. So, when the small and large crystals are both present in a solution, the smaller crystals will dissolve and the larger ones will grow until the smaller crystals disappear. And this phenomenon is called as, most popularly, Ostwald ripening. What are the factors which affects the rate of growth of crystal? The number one factor, temperature and concentration of the liquid at the crystal face. These conditions are not generally the same as those in the bulk of the solution because concentration gradient is necessary for the transfer of solute towards the face. Temperature gradient for the precipitation of the heat of crystallization necessary. Thus, problem involves both heat transfer and mass transfer. Thus, the concentration gradient is the driving force for the crystal growth. Second most important factor is the rate of agitation. The rate of crystallization is improved by increasing the rate of agitation. The crystallization rate initially rises very rapidly by increasing agitation, but point is reached where further increase in the agitation produces no effect on the rate of crystal growth. Third most important factor is the degree of supersaturation. This increases the crystallization rate. Fourth one, that is the presence of impurities. Any foreign solid bodies acts as a nucleus and enhances the crystallization. Viscosity is also imparting effect the crystal growth, that is, as the viscosity increases the rate of crystal growth decreases because the viscosity decreases rate of diffusion of solute to the crystal surface. The crystal habit is affected by the presence of impurities, temperature variation and a degree of supersaturation. Dear friends, up till now you have gained the brief idea about what is crystallization, what are its applications, nucleation, crystal growth. If you have missed any of the module or content, you may log on to our website www.cec.nic.in to download videos, FAQs, LOR and other content so that you can remain updated with this chapter. Now let's move ahead to a next module, that is about crystal type. Module 3, that is crystal type. Crystal is a solid particle formed by solidification process in which structural units are arranged by fixed geometric pattern or lattice. Characteristics of the crystals. Crystal lattice, orderly internal arrangement of the particles in three-dimensional phase. The geometric form in which structural units are arranged in a crystal is determined by X-ray diffraction pattern. It is a set of infinite arranged points related to each other by transitional symmetry. The outlines of such patterns are called as lattices. Lattices are comprised of intersections of three parallel planes. Characteristics parameters to describe the crystals are as written below. Space lattice, three-dimensional arrangement of the particles in the crystal. Unit cell, smallest geometrical portion which repeats to build up the whole crystal. Then what is faces? That is plane surfaces to which the crystal is bound. Axial angle, angle between the two perpendiculars, two intersecting faces. Axial length, that is distance between the centers of two atoms. crystal systems or forms. Finite number of symmetrical arrangement possible for the crystal lattice. These are 7 classes of crystal systems, forms, also known as crystallographic systems. Depending on the axial length and axial angle, crystal forms may be designated as 1, that is cubic form, 3 equal axes at right angles to each other, for example sodium chloride, potassium chloride. Tetragonal form, 3 axes at the right angle, one longer than other two, example urea, potassium dihydrogen phosphate. Orthorhombic form, in which 3 axes all at the right angles but all of different lengths, example barium sulfate, sulfacetamide. Then fourth is the most important, that is a monoclinic one. Monoclinic form, 2 axes at the right angles in one plane and third at some odd angle, example sucrose, ephedrine hydrochloride. Fifth one, that is a triclinic, 3 angles at odd angles to each other, example phenolphthalein, copper sulfate. Sixth form is a trigonal form. The 4 axes, 3 are equal in length and lie at an angle of 120 degree from each other, and the fourth is either longer or shorter but must be at the right angle towards the other corners. Crystals in the rhombohedral lattice system are always in the trigonal crystal system, but some crystals such as quartz are in a trigonal crystal system but not in the rhombohedral lattice. Quartz and bovine, rhodopsin are the examples of that. Hexagonal, the 3 equal axes in one plane at 60 degree, one at right angle to this plane, best example is the thymol. Let's move towards the crystal habit. The morphology of crystalline form is often referred to as its habit, where the crystal habit is defined as having the same structure but a different outward appearance, or alternatively the collection of faces and their area ratios comprising the crystal. Depending on arrangement of faces, crystal habits are described as columnar crystal habits, that is prismatic one, rod-like particles having the width and thickness exceeding that of needle type particles. Second, blade type of morphology in which long thin flat particles. Third, plate lamellar in which flat particles of similar length and widths. Fourth one is tabular form in which flat particles of the similar lengths and width but greater thickness and flex. Fifth one is equant, particles of the similar lengths, width and thickness. Sixth one, that is acicular one, needle like prisms. Having understood the concept of crystal growth and nucleation, let's move on to the theory of crystallization in detail in module 4. Theory of crystallization is explained by Meyer's supersaturation theory. The theory postulates a definite relationship between concentration and temperature at which crystals will spontaneously form in an initially unseeded solution. Supersolubility curve represents the limit at which nucleus formation begins spontaneously and the point at which crystallization starts in the absence of any solid particles. As in front of you, the supersolubility curve, that is curve AB and curve FG. Two curves are there. By plotting the graph of concentration versus temperature, in which curve AB represents normal solubility curve. Any point on the curve represents solute in equilibrium with the solvent. It is the maximum limit for the solubility of the substance. While the curve FG representing supersolubility, nucleus formation begins spontaneously. It is the point where the crystallization can start. It is called as stable zone, which is well defined zone below the solubility curve. The unsaturation prevails and crystallization is not possible. In between the two curves, there is a region which is known as a metastable zone. Metastable zone is a region between the curves AB and FG. The Mears theory points out that greater the degree of supersaturation, the more chance is of nuclei formation. And second, if the supersaturation passes a certain range of values, nucleus formation is very extremely rapid. The theory can be explained with the help of, again, with the solubility and supersaturation curve. The supersolubility curve, in which curve AB is a solubility curve, normal solubility curve, which represents the maximum concentration of solute that can be obtained by bringing the solid solute in equilibrium with the solvent. If the sample of the solution having the temperature and the composition of the point C is cooled in the direction of CD, it first crosses the solubility curve AB, but no nucleus will be formed. When it reaches somewhere in the neighborhood of the point D, according to Mears theory, crystallization begins. As the crystallization proceeds, the crystallization of the solution follows roughly according to the curve D and reaches the solubility curve. In the absence of any solid particles, the curve FG represents the limit at which nucleus formation begins spontaneously and consequently crystallization starts. This line FG is called as supersolubility curve. According to Mears theory, at any point between the C and D points, nuclei cannot form and the crystallization cannot occur. Now, we will go for the conditions for the obeying Mears theory. Most important condition, first condition, that is the solute and the solvent must be pure. The second, the solution must be free from solid solute particles. Third, the solution must be free from foreign solid matter. Fourth, the solution must be protected from the entry of any particle. Fifth, that is a soft or weak crystals must not form during the process. There are some limitations of Mears theory. Limitations like 1. That is crystallization starts at the supersolubility curve, but crystallization takes place in any area rather than line. Second, if the solution kept longer periods, nucleation starts well below the supersolubility curve. Third, if the solution is available in the larger volume, nucleation starts well below the supersolubility curve due to collisions of molecules. Fourth, applicable when pure solute and pure solvents are used. Fifth, during the storage, dust particles can enter that may initiate the nucleation. The conclusion: crystallization is the chemical solid liquid separation technique in which a mass transfer of solute from the liquid solution to the pure solid crystalline phase occurs. In the formation of crystals, three major steps are essential: supersaturation, that is the formation of concentrated solution; nucleation, that is the birth of new solid particles; and the crystal growth, the growth of the nucleus to the microscopic size. The topics deals with the characteristics of the crystals and the crystal habit. The theory of crystallization is explained by the Mears supersaturation theory. The theory postulates a definite relationship between the concentration and temperature at which crystals will spontaneously form in an initially unseeded solution. Supersolubility curve represents the limit at which nucleus formation begins spontaneously and the point at which crystallization starts, in the absence of any solid particles. In the brief, the topic gives the precise overview of the basics, applications and theory of crystallization phenomenon. With all these information, here we come to the end of today's class. Do keep in mind what we discussed today. Time for you to do the self-study. This is Swapnil Patil signing off. I will be back with one more lecture in this series. If you want to learn more and enhance your knowledge, you may log on to our website for the MCQs, quiz and LORs www.cec.nic.in. Till then, keep studying. Goodbye.